Hey YouTube, it's Dimitri. Today I just want to give you guys a little bit of intuition behind decision trees here as we kind of get going on a few different examples and a few different topics here. I want everybody to really understand these, not from a math perspective and not from a coding perspective, but really just what we're kind of doing and how we are solving business problems with decision trees. So to start off with here, let's just list out what we call these things in general. So we call these things cart, and cart models, or I don't know what else you'd call them, cart models are going to be classification and regression trees here. So this is going to be the most simple form of decision trees here. Now, if you want to get more complex and more fancy, the other thing you could look at is, gradient boosting decision trees. There's also other types of these. So for example, there's like light GBM. So GBM. So these are considered as gradient boosting models. So GBM. So gradient boosting decision trees, you could call them, I've never seen it, but I guess you could call them GBDT. I'm sure somebody's put it out there. But light GBM is just another sort of calculation or math. Some people call them algorithms in the computer science world. I put his little air quotes to get to that. You also have random forest. And I'm sure there are other ones out there, but they're all just decision trees. So we're just going to stick with our cart model here. And we're going to focus specifically on classification for this video and a few examples. And perhaps maybe we'll touch on regression. I don't like regression for decision trees. It's probably the most inappropriately used form of decision trees for most situations. In future videos, we'll talk about why linear regression is actually far better than using decision trees. All right, so before we get started here, let's just build a business problem so you guys can kind of see how these kind of come through the pipeline, because this is what really happens is a business comes in and says, Dimitri, I need to model, let's say, probability of default, because as you guys know, this is my favorite model because I've done this so many times. It is easy to come up with quick examples for probability of default. And the way this works is you would set up some sort of definition here of defining default here. Let's say these are for auto loans, and let's just define default as charging off. So the customer hasn't paid the loan. They're not going to pay the loan. They've defaulted in the sense that they're done. So we typically say this is 120 DPD. This is just, days past due. Now you could define your dependent variable. So this is going to be our dependent variable. You could also define this as like 30 days past due or 90 days past due or 60 days past due. Like you could define it any way you want here, but essentially 120 days have gone past and the customer made no payment. So we're going to go out and repossess this car. Often the customer just brings the car back because I've sent them a bunch of notices and said, hey, you owe me this money. You never paid me. I need the asset back for this. And so what we do is it's just probabilities here. So this is going to be either a 0 or a 1 in this sort of event here. 0 is going to be they made a payment, or they are not. So I guess the correct way to say this is they are not 120 days past due. So, maybe they're 90 days past due or 95 days past due or something else, right? They have not met the definition here, so they are just a 0. And then 1 is going to be that they actually defaulted. So this gives us a probability, right? They're 0 or 1. So we go through our data here. We look at all of our customers. So let's say you have, a customer ID in our data here, and it has, C75219, C82135. You have a bunch of these customer IDs that go down. And all we're going to want to look at right now is we're going to create this variable called default, and we'll put it here. And we're going to go through and look and say, okay, how many days past due was this customer over the life of the loan? It might be 0, 0, 1, 0, 1, 1, 0, 1, all the way down. And this is going to be the dependent variable that we're actually modeling here. Now, when you're a business, right, the question typically is you don't care about any of this. The question is going to be, what can I do to prevent defaults here, right? So from a business standpoint, right, we don't want customers to default because we lose money. So what we want to do is we want to find good customers that are not going to default so that I can have a better profit margin here, right? This is what the business wants to know. Now, the question they really want to know is how can I prevent that? So what they're really telling me is they're really asking, what levers, what variables, so levers, variables, can I adjust to prevent, or more specifically, to reduce or to minimize here, reduce defaults. And typically here, the business should give you some sort of insight, or you as a quant should have some insight, or a data scientist. Things that we know, for example, is LTV. So LTV is going to be the ratio of loan to value here. So let's say you make a $10,000 loan on a $20,000 vehicle. You have a 50% LTV. This is pretty safe because what happens is if the customer defaults, right, and they only borrowed $10,000, and if the vehicle is still worth $20,000, I can go repossess that car, sell it at auction, be made whole. The fact I'll get my whole $10,000 back, or whatever's remaining on that loan they didn't pay, and then the rest of the money will go back to the consumer because it was such a safe loan here. Now, could be the other way around. Could be a $20,000 loan on a $10,000 car. Now, we'll put the example over here. If you had a $20,000 loan over a $10,000 car, this is 2.00 here, meaning it's a 200%, as we call it in LTV terms, a 200% LTV, which means if they defaulted the first day with zero payments, I'm going to get $10,000 back. Hopefully, typically it's you actually collect less. There's fees and all kinds of other stuff that ruin it. But you're gonna get $10,000 back because that's what the vehicle's worth. But they had the loan for $20,000, so you automatically take a $10,000 loss on the car. Okay, so now you're gonna be wondering, Dimitri, this is dumb. Why would anybody take an LTV less than or greater than 100? Well, when you have principal, this is the principal piece. If they pay this in full, you get the $20,000 back, but you also have interest, and interest is going to comp you even more than that. It's comping you for taking the risk of the loan here. So the amount of interest rate that you charge, the APR, should help cover the APR is used to get the amount of interest you collect on this loan. And we need this model to tell us who's likely to default and who's not likely to default. And so one thing we're going to look at here, as I mentioned, is going to be LTV. Now, other possibilities, let's say, is PTI. This is payment to income. So this should be fairly obvious, right? If your payment on your loan is very small and your income is very large, so, and this is small, this is going to be equal to a low risk. Or more specifically, right, this is going to be a low PD, low probability of default. When your payment is huge and your income is small, this is going to be a high risk. So when this is high, risk is going to be high as well. Or more specifically, because we're going back to this problem here, I'm defining risk as probability of default, and so PD is going to be high. So let's just start off here with this example, and let's just take LTV. This is going to be what we call our independent variable. And PD, which we already defined as 120 days past due, is going to be our dependent variable. And so what we're saying by this is that this PD is dependent on the list of independent variables we have. We can have a whole list of independent variables, which are variables that are driving or predicting our probability of default here. But for the decision tree for the CART model, so more specifically the classification decision tree here, I'm just going to use one variable. So this is a univariate case because it is much simpler to understand and get the intuition of what we're trying to do here. But what we're trying to do is you'd plot this out and you would see here, okay, we have, so this is going to be 0 and 1. This is our PD. And then we're going to have LTV on the other axes here. And LTV can range from 0, I don't know, let's say on our sample size here, we ended up with 200, which is really 2.0. LTV up to 2 times. So that's a pretty crazy LTV to have, but we have it on this chart here. The way our data is probably going to look is we're probably going to say, okay, really low LTVs have low probability of defaults, and they can only take the value of 0 and 1. So it's going to be, something like this. Like there's a bunch of them down here where these LTVs are, I don't know, let's say like this is like, 0.50. and there's a bunch in here, and then all of a sudden you're going to have maybe a couple, right? Life happens. Like the guy that had, I don't know, the 0.48 LTV right here. Let's say this is, I don't know, 0.48. This guy got a divorce and he didn't have the money and he lost his job and life sucks. And there's going to be a few people that are kind of in here. And then you're going to have a few people out here that like, you know, had crazy high LTVs and paid off these loans because, I don't know, maybe they're a drug dealer or something. They didn't report their actual income, but they've got a ton of cash and it's not legal or whatnot. And they made this sort of payments here. I don't know. Maybe these people are just great people too. Like they're just so dedicated to making these loans. And even though they're getting screwed because they're in a bad situation, which occurs. So small finance companies take advantage of poorer customers, whole other thing. What we're going to do here is the majority though of these data points are going to be clustered in this section where we have, you know, high LTVs. And of course we're going to have, like I said, some overlap in between them in general. But really what we're seeing here is we start to see that there are pockets, right? There are multiple pockets kind of, and you might end up noticing there are different groups here. And the entire intuition of a decision tree is answering the question, how do we split up, or more specifically, cluster individuals based on LTV to predict PD, probability of default here. Right. So you might start to think about this from a business standpoint. Maybe you have a policy here, right? Maybe you're going to say, I don't know, maybe you're going to approve on this, reject on this. Maybe you're going to say, okay, we're going to approve loans that are less than a value. And we're going to reject loans that are too risky, that are too high. Or you might say you're going to give different APR. Let's say you do this for APR pricing here. So let's say pricing is APR. You might say we want to figure out what are the pockets and groups of performance here. And we want to figure out the groupings, and then we can back into this using some accounting here to figure out which rate to give them. But we need to know who's performing how. So what we're going to do is, I'm not going to do the math here for you guys. We'll do this in another video. I'll try to use the same example here. We want to say, okay, this pocket seems to have a probability. So the probability of the event, which in our case, the probability of PD here is just going to be equal to, in this pocket, right? So this is kind of the divisor. We have 1, 2, 3, 4, 5, like six zeros here. So the probability of default, there's 6 down here and there's like 3 up here. So there's a total of 9. So 9 goes on the bottom. How many of these had an event? How many defaulted? Looks like there's 3 up here. So it'd be 3 over 9, and this is going to be 1/3, which is equal to 0.33%. So this has a default rate of 33%. Okay. And then you might look at this and say, okay, maybe we end up having like, this is like another pocket for some reason. And I'll do the math later on how we get to these splits here. But again, this is going to be this region. And so there's 1, 2, 3, 4, 5, I don't know. There's like 5 data points here, but there's 1, 2, 3, 4, 5, 6, 7, 8, like maybe 9 down here. So this is going to be 14 in total, 5 on top. And this gives us 35.7%, something like that. So 357. And then we look at this final grouping here. And it looks like there's 2 groups, right? I mean, this seems like to be a pocket here. Maybe you have some split in the middle. And so we're going to count these. There's 1, 2, 3, 4, 5. Like, I don't know, say there's 6 here and there's 2 down here. So now this leaf, this next one. So the third group is going to be 8. So 6 over 8, which is going to be 75%. And then finally, this last group, you know, here in this region here, these 2, we have 1, 2, 3 on the bottom. We have 1, 2, 3, 4, 5, 6, 7, like 8 on top. So the last group's gonna have 11 in total. It's gonna be 8 over 11, which is gonna give us 72.7, so 0.727, which is, you know, 72.7%. So you can view these in decimals or percentages here. So this would be 35.7%. But another way to view this though in a decision tree is the actual tree amount. So you might say, okay, you know, if LTV is going to be less than, and let's say this line here is, I don't know, like 1. Let's just say this is 1.00. If LTV is less than 1.1, it's going to go this direction. So this is what's called the trunk of the tree, I believe. So if LTV is less than 1, it's going to go this way. So this is yes. And then if it is no, it is greater than that. What we're going to say is it's going to have another leaf. Okay, so that'd be 2 groups here. Well, we have 4 in total. So now the next rule is going to be, let's say this is 0.25, and this split over here is, I don't know, 1.25, because you can see there's more space here. I don't know. We're just making stuff up. But what we're saying here is, yes, okay, if the LTV is less than 1, it's going to be in this region. So now we're saying if we're in this region here, or this region here, which are going to be these next 2 splits, we're going to say, is LTV less than 0.25? And if it is yes, it is going to be leaf number 1. So this is 1. And if it is no, it'll be in leaf 2, which will be here. And then, of course, on this right split here, again, looking at the areas here, if we have anything that is greater than, so where this, put a line here, anything greater than 1, it's going to fall somewhere in this half, okay? Somewhere over here. And then we're going to split that again, and we had that LTV of 1.25. So is LTV less than 1.25? If it is, it's going to be leaf 3. So say yes. And if it is a no, it's going to be leaf 4 here. Okay, so this is leaf 3. This is leaf 4. Now, I really, really want you guys to understand there are 2 perspectives here on how we're looking at the tree here. So this really pretty thing here, this is really a decision tree, right? It is a tree, and it's really just a list of if statements. So you can implement this in Excel, okay? You can implement this in any sort of simple tool, right? If LTV is less than 100, it goes down this stride, and you can write basically 4 rules, right? So if LTV is less than 0.25, it's going to be 1. Now, 1 is going to be the average of the data points in that leaf here. That's what we calculated out over here when we said, 0.33. The average of the events here that are actually occurring are going to be 0.33. And then we went on to do leaf 2, and leaf 2 is going to give us, I believe, the 0.357, and leaf 3 was going to give us 0.75, and leaf 4 is going to give us 0.727. So these are the values. You can clearly see that on a business standpoint, you could easily write out a list of rules for your sales staff here. Like maybe you strategically say, okay, these customers in leaf 1 are the safest. They're going to get an APR, I don't know, say 7%. Leaf 2 looks even safe, looks a little bit more risky, right? But not a lot. So let's say this is like 7.25%. And then finally for leaf 3 and leaf 4, you can see leaf 4 is actually safer than leaf 3. So it's nonlinear. So what we could do is say, okay, this is going to be like 8% for leaf 3 here. And then leaf 4, we might do, 7.75%. So all we're doing with the decision tree is taking a population, which is going to be this piece here. This is the population. More specifically, so cross that out. This is the sample space view. And I think this is very helpful to see and understand this because you have a space, right, area, and we're just figuring out how do we slice and dice this up now. If we had another variable instead of LTV, we had LTV, right? And we also had, I don't know, like PTI, which is the other one. You could think about this as a 3-dimensional cube, and we're just slicing up square areas based on these rules to say who belongs in what group here. The other example on this side here, this is, as I mentioned, this is the actual decision tree kind of perspective on this. But both of these tell you the exact same story, but I hope you guys can get a little bit of the intuition here, which is we just have something we're trying to model. We want to figure out how do we divide that up into groups so that we can make better decisions, right? We're trying to answer this question here, which is going to be, how do we split up or cluster individuals based on LTV to predict PD, which is really going to be, we're predicting our risk here so we can apply like an APR in this example. And then if we extend this now, as I mentioned, more into a 3-dimensional case here, things get complicated, right? So I'm trying to show you guys this in a 2-dimensional space here because it's very easy to see the sample space view, and it's very easy to see the decision tree view. But a decision tree could have, LTV less than 1.5, which could be the first split. Then it could say, okay, if that's true, you could have PTI less than, 0.15. That's another split. Then you could have, if it is a Honda manufactured vehicle, then this would be leaf 1. Then you might have, if it's not a Honda, it's a 2. And then you might have, if PTI is greater than 15, this is just leaf 3. So you notice it's not symmetrical, right? There's not another box right here, and there's not, some other leaves hypothetically down here. Your trees don't have to be symmetrical. And you might even have a really lopsided tree and say, okay, let's say we have, again, Honda. So if it's a Honda, maybe Hondas don't break down that often. And so they help predict the risk of you actually completing the loan, because when a car breaks down all the time, you're not going to have money to actually pay the loan because you're always fixing the car here. You then might have, some outcomes like leaf 4, and maybe there's another box. We'll just call leaf 5 here. We'll have some tree like this, right? But now when you start to think about this in a, that sample space kind of view here, it has to all of a sudden start to get kind of wonky, because if it's 3 dimensions, then you would have, probability of default, which is what we're modeling. And then you have LTV. So that's, LTV is number 2. So this is 1 dimension. This LTV is 2 dimensions. PTI is 3, and Honda is just 4. So Honda can be played in multiple parts of the same tree. So again, you can have variables in different parts of the tree and different rules. And really all we're doing with decision trees, though, should be viewed in this sample space, that we're just segregating groups of people, more or less. This is what models do, right? You look at a bunch of characteristics and we segregate people into group 1, group 2, group 3, group 4, and group 5. And we're just trying to get everybody into the proper groups here. Now, segregation is a nasty term, especially in US history. This is why you don't just throw crap into trees and hope like hell it all fits. You actually have to go, okay, right? Dimitri is explaining to me why LTV would drive probability of default, why Honda could drive this, why PTI could drive this. What you don't want to see from a business standpoint is you wouldn't want to see, let's say, a split like here that says your education, which, this is like a gray area, but really if you wanted to violate a bunch of laws, you'd have like race, or you'd have like religion, or you'd have just nonsensical things like how many websites you viewed, had some sort of product in it. Like for me, these get to gray area. So these are big no-nos, right? But when you get to things like education, maybe criminal status, maybe that's a bad example, but more specifically, like what hobbies you have, right? Your hobbies, should have no bearing on your probability of default on an auto loan. So they shouldn't be in the model here. So again, it takes some intuition. It takes the business insight to really build a good, solid decision tree. But we're just trying to figure out, how do we split up, these kind of areas here. And I can't even draw in 3 dimensions very well, but how do we create these groups and pockets so that we can actually predict something and make good rules for the business, so the business can make good decisions and actually be helpful to the business side here. So I hope you guys found this helpful. This is just trying to get you guys to kind of wrestle with the idea of what a decision tree is. And then I'll break out some more videos on doing some math and kind of breaking these things down in a bit better detail here. So anyways, if you found this video helpful, please do like, share, and subscribe. And as always, until next time.